Hello, is the sound better now? Am I audible? Can you guys please give a thumbs up if the sound is okay? Okay, I'm trying to fix it. Hello, hello. Am I audible now? It's working fine? Okay, great, great. And like, has somebody cross-checked on YouTube as well? Like, whether it is working fine on YouTube? Okay, great. Yeah, apologies for the technical glitch. Okay, so sorry. So the topic for today is queries on trees in Div 2. Like in the Div 2 track, we have discussed on, I think day one, we introduced segment trees. On day two, we discussed square root decomposition. So the audio is lagging. Somebody saying that the audio is lagging. Is that the case? Do you guys think the audio is lagging? Okay, okay, okay. No worries. So it's probably an internet issue. Okay, some people are saying that it is lagging, some people are saying it's not lagging. I imagine that it might be an internet issue on the receiver's end. Maybe I can try to change my internet connection. Okay, so anyway, okay, so let's get started. So like today we want to look at scenarios where so like I assume that now after attending the lectures on day one and day two, we already understand how to do say point updates and range queries on a like on an array. But now like let's also like in today's lecture we will try to look at how can we do point updates and range queries on a tree. And first of all, like we'll also define like what it means to do a range query on a tree. But yeah, let's get started. So as like some of you might already know, I'll just quickly repeat it for the sake of completeness. The way I'll take this lecture is that I will change my like I will present my screen and I will show you guys some slides where I will also be writing. In order to address the questions and to see your comments, I will change my screen back. Like I will take breaks in between and like change my screen back to the chat box and ask you guys questions. Okay, so in case you have any doubts, uh, please keep asking them in the chat box. Like some of you are asking the topics that we will discuss. Uh, that like the topics would be how to do queries on trees. So more concretely, heavy light decomposition and Euler 2 technique. And then we also look at how we can combine both of these to get one single powerful method to do queries and updates on both paths and subtrees of a tree. Okay, so like I will share more details on this. Don't worry about it. So let's get started. I'll share my screen now. Can all of you see my slides, which says queries on trees? Uh, so I'll quickly change. Okay, great. Okay, so let's get started. The objective for today's class is to understand how we can support queries and updates uh, on trees. Like first, we want to look at what different types of problems exists. Like what are the different category of problems where we might be asked to do a query or an update on a tree. Like the two most famous ones are say the path query and update problem and the subtree query and update problem. So we'll define what these problems mean, and then we will discuss techniques to handle both of them. Like first we will discuss what is known as HLD, like heavy light decomposition. So this technique is like very useful to answer path query and update problems. Like we will discuss its theory and also take a brief look at its implementation. Then we will discuss like what is called an Euler 2 technique. Like this is also another way to support queries and updates on trees, and it is primarily useful to support subtree queries and subtree updates. Like we will define what that is. Again, we'll look at the theory and implementation of this technique, and then we will also look at how we can combine. HLD and Euler tools into one single way, like into one single method that can support both path queries and updates as well as subtree queries and updates. So it will be a very like powerful way to tackle almost all kinds of query and update problems on trees. And then later on, like I've just mentioned this for the sake of completeness, I won't go into the theory of these topics here. There are some other techniques as well which can be used for like queries on trees. For example, centroid decomposition. I discussed this in a Div 1 lecture yesterday. Uh, so like maybe some of you can take a look at it once you master these techniques discussed in today's class. And like there's also another trick known as auxiliary tree. Yeah, I don't think we will have time to go into the theory of this method as well, but I have given links to some relevant readings that you can do in case you are interested. Okay, so this will be the objective for today's class. The class might be a bit heavy, so like please try to stay attentive and follow as much as you can. And in case like you miss out, like in case you miss out on some details, you can always watch the recording later, or maybe take a look at the reading materials and code pieces later on. But this is a really important topic that can like help you expand your toolkit quite a bit. Okay, so let's get started. Sorry. So first we define what is called a path query and update problem. So a path query in a tree means so like as you guys would already know, a tree is a graph which has like no cycles, like and is connected. Okay, so like you can represent a tree like this. So like a tree has two different concepts. It has a concept of a path where you give any two nodes, say x and y, and there exists a path between these two nodes. There exists a path between these two nodes. Okay. So if you look at the example which I had drawn, I've marked nodes x and y, and I have marked the path that exists between x and y. So a path query gives you two nodes x and y, and it asks you to compute some function f of xy that depends on the path between the nodes x and y. Okay, this function f can be different for different problems. For example, like some examples of what this function could be is say sum. It can ask you to compute the sum of nodes which lie on the path from x to y. So therefore, the sum of this node plus this node plus this node plus this node plus this node. So every node could have a value. Or it could ask you to compute the sum of edges which lie on the path from x to y. So the sum of edge weights of all these edges. Okay. Or like the function could be anything else. For example, it could ask you to compute the minimum weighted edge or the maximum weighted edge or the number of distinct elements that occur where every node has some value, and you want to know the number of distinct values which occur on the path from x to y. So like you can have all different kinds of simple and complex functions that you might want to compute, but this is what we mean by a path function. Okay. So, like this is the kind of queries that we will encounter when we say a path query. A point update in a tree could be like could ask you to change the value of any one edge or the value of any one node in the tree. It could give you a node comma value and ask you to assign the new value, or an edge comma weight and ask you to assign a new weight to that edge. And you would be asked to support these query and updates simultaneously, similar to how we have done that in like how we have done this in say the segment trees class or in the square root decomposition class. Okay, but there we did this on linear arrays. Now we have to do this on these complex trees which have a very different structure than arrays. And similarly, you could also have range update problems where say you could be given a pair of nodes x and y, and you could be asked to change the value of all nodes or all edges which lie on the path between x and y. So for example, you could be asked to add a value x to all edges that lie on path between x and y. So you need to do a range update. You want to add value x to all of these edges. Okay. So these are just the different type of queries or updates that can occur when we say we are dealing with path queries and update problems. Okay, is this clear to everybody? Any doubts so far? Sorry. Okay, great. So, like Aryan has a question that path will be order height of tree. It depends on the problem or the algorithm. But yeah, if you naively try to do it, it could be order number of nodes in the tree. Like today's topic is not like is somewhat related to yesterday's topic because you can use the techniques discussed yesterday, but it is also a very independent topic in itself. So, if you haven't seen yesterday's class, it is still okay to stay focused on today's class. Okay. So next we have like what I call subtree query and update problems, where you want to do some query on the subtree of a node. Okay. So earlier we saw like what I called path queries. Now we are seeing a different type of query, which is called a subtree query. And the format of this query is such that you are given a node x and you want to compute some function f of x that depends on the values of all nodes or edges that lie in the subtree of x. Okay. So as I discussed earlier, uh, a tree has a shape like this, and the tree has a concept of a subtree. So a node. So if you have any one, if your tree is rooted, which means that you take a node and you pin it on the wall. For example, this node one is the root of your tree. Then so you can imagine rooting a tree as taking a node and pinning it on the wall, and because of gravity, all other nodes would start pointing downwards. So the tree would look something like this. Like this is a rooted tree, which is rooted at node 1. So if you root your tree, every like there's a concept of subtree where every node, like a subtree of a node would be all other edges and nodes that lie below it, or for example, like for whom this node is an ancestor. Okay, so in this case, for example, all these nodes and like all these two nodes and edges lie in the subtree of the red node. The nodes and edges in the blue box lie in the subtree of the red node. Like this is a very basic concept. I assume like most of you might already know this. Like I'm just repeating this for the sake of completeness. But yeah, like now a subtree query could be, for example, given a node x, like let this be node x. I want you to answer the sum of the values of all nodes that lie in the subtree of node x. Okay, so you will have to return me the sum of values of all nodes that lie in the subtree. So therefore, like the sum of this node plus the sum of this node plus sum of this node. Like you want to return the sum of all of these nodes. In this case, the number of different nodes are only three, but you could have a lot of nodes in the subtree as well. For example, if you take a tree like this, and I give you this node x, and I want, like I ask you to return the sum of elements in the subtree of this node, then you would have to return the sum of all of these nodes. Okay, the sum of all of these nodes. So these are what I called subtree queries, and they are different from path queries because in path queries you are given x and y, and you want to return the sum of nodes on the like which lie on the path from x to y, and in this case you want to return the function value for all nodes that lie in a subtree of a node x. Okay, and again, like the function f could be arbitrarily complex. Like for example, it could be some minimum maximum number of distinct elements, etc., etc. Okay. uh, and again, like there could be a point update which is very similar, that given a single node or a single edge, you want to update its value. Or you could also be asked to do a subtree range update. For example, you could be asked to change the value of all the nodes or all the edges which lie in the subtree of a node x. Okay, so for example, you might be asked to add a value val to all nodes in the subtree of x. So then you will have to change the value of this node, this node, this node, this, everything. So you will have to do an update on all of these values. Okay, is this clear to everybody? Okay. So far I'm just defining what our problem is. Subtree can contain the node as well. Yes, like when you usually talk about the subtree of node X, like you talk about the subtree rooted at node X. So it also includes the node itself. So for example, if you consider a leaf node, like the leaf node would be I mean the subtree of the leaf node would have a single node, which is that node itself. Okay. Sorry. So now the question is that how do we support these updates and queries on a tree? Okay. So based on the previous lectures that we have attended, say segment trees or square root decomposition, or even if you have not attended, like you can assume that if you are given a single array A, if you are given a single linear array A, so an array is a linear data structure, which means that like all the like there's a simple ordering between the elements, and you can identify like any element by only its index. Whereas a tree is a non-linear data structure. In a tree, like there is no straightforward ordering between the elements. Like it is a complex structure, right? So if you are given a single array A and you are given say point updates or range queries, like you are given an LR and you want to do some range query, you know how to do this. Like you know that you can use segment trees or you can use square root decomposition or any other technique for answering these queries. So you know how to do range queries and range updates, like point or range updates on an array, which is a linear data structure on an array. Okay. So now, but we have to extend it to do it on tree. So the way we support these updates and queries on tree is that first, like the step one is like we try to find a way to linearize our tree, which means that we try to find a representation of the tree in the form of an array. Okay. So because we already know how to do these things on an array. So if somehow we can represent our tree as an array and we can represent the update or the query that we need to do, if we can represent the query or update as a continuous range, as a continuous range LR in the array, then we are done. Okay, then we are done. Why? Because we already know how to support this. We already know that given an array and a continuous range L comma R, how to do a point update or the range query or the range update. We already know these things. Like if you don't know them already, like you can assume that there exist ways of doing this which are trivial and like not trivial, but it is a separate topic which is well researched. So like there are standard techniques to do this. Even if you don't know segment trees, if you haven't attended the previous classes, you can assume that segment trees exist and they can help you support range queries and range updates on a continuous segment LR of a linear structure like an array. Okay, but so to support path queries or subtree queries, the first step is to find a way to linearize the tree, that is, represent the tree in the form of an array with this constraint that after this representation or after this linearization, you should be able to represent any query or update that you want to support as a continuous range L comma R in the new array that we have formed, in this array that we have formed. Okay. And to do this, there are these two different techniques which we want to discuss. The first technique to linearize the tree into an array is called heavy light decomposition. So this technique will help you linearize the tree such that any path from x to y can be represented as a concatenation of at most log n different L comma R ranges in the linearized array. So instead of representing any path from x to y as a single range, you are representing that as at most log n different ranges. At most log n different ranges. Okay, and this is still fine because you can use your segment trees or any other like data structure to do log in different queries on the array or log in different updates on the array. Okay, so it will add a multiplicative log factor, but it should still be good enough complexity. And similarly, we have what we call an Euler 2 traversal. An Euler 2 traversal will linearize your tree such that any subtree of a node x, any like for any node, the subtree of that node will correspond to a single range L comma R in the linearized array. So this works well. So like using Euler tree, you can have a one-to-one mapping between subtree of a node x and some continuous range L comma R in the linearized array. So whatever query or update you want to do on a subtree, you can simply do it on the linearized array. And that is the beauty of this Euler 2 technique. So both of these techniques, notice, are just a way of converting your tree, like not converting, representing your tree in the form of an array. Like using some smart ways, you want to represent your given tree in the form of an array, so that you can use the standard techniques to support like range updates and range queries on an array. So okay, so the next step, like as you guys can see, is to use one of the standard techniques to solve the update or query problem on the linearized tree. And these standard techniques could be segment trees, it could be square root decomposition, it could be persistent segment trees, it could be BIT, it could be anything. Okay. So step two can be an independent topic it's in itself. Like today's lecture will focus only on step one. Once step one has been done, you can use any of the hundreds of toolkits which are available in computer programming to solve step two, depending on what the problem is. Okay. So it is important to understand that step one is doing something different, and step two is doing something else, which is and step two is another standard technique which is beyond the scope of this lecture. That how to actually support the updates or queries, but rather today we'll focus on how we can actually linearize the tree so that we can use one of the existing techniques to solve the ranges query and update problem. Okay, is this clear to everybody? So I'm taking a look at the chat box quickly. Okay, I will explain my examples as well. Don't worry. Okay. Uh, is it clear so far to everybody? Like so far, I've just explained what we are trying to do. I have not explained any particular method of how to do these things, but I've only talked about what we are trying to do. Okay, so please be please don't worry. Like we, I mean, this is not the end of the lecture. Uh, log of n is like is a function. Like log is a function, so log in is a multiplicative factor. But yeah, like maybe you can watch div 3 lecture on complexity theory to understand more about it. Okay. Okay, so let's look at the first method. So the first method to break the tree, I mean the first method we discussed today is the heavy light decomposition. Okay, the heavy light decomposition. So again, remember the objective of what this is trying to achieve. So far, I have tried to motivate that what we are trying to do, and now we are moving on to the discussion on how to exactly do it. Okay, so it should be clear that we are trying to linearize our tree into an array. Like we want to find some representation of the given tree in the form of an array. Okay, that is the objective. Okay, so the first way to linearize your tree is what is called as heavy light decomposition. Sorry. So the technique goes as follows. We say that we want to like we will break the given tree into vertex disjoint chains going from top to bottom. Okay. So what we do is that for every node, for every node, like we have some children of the node. For example, like this is a child, this is a child, this is a child, this is a child. Okay. We have some edges going down from the node. Among all the edges that go down, we will mark one edge as a heavy edge. For example, in this, like for the first node, this particular edge is marked as the heavy edge, and every other edge is marked as a light edge, as a light edge. The edges which are uncolored in this picture are examples of light edges, and the edges which are colored are examples of heavy edges. Okay. So from every node, we choose one of its child nodes and we mark the edge connecting that child to be a heavy edge. And rest of the edges are marked as light edges. Okay. So if you continue this procedure for this node, we have like we select this node to be a heavy node, mark this edge as heavy edge, mark everything else as light edges. Okay. Similarly for this node, we mark this node as a like this child this edge as a heavy edge, and therefore the corresponding node as a special child, and mark the rest of the edges as light edges. This is a light edge, this is a heavy edge. Again for this node we have one heavy edge, other is the light edge. We have a single edge which is a heavy edge. Okay, so for every node we have one heavy edge going down, and the child corresponding to the heavy edge is called a special child. It is called a special child, and the rest of the children are called normal child. Okay, so this is just the terminology. I'm not like don't worry, like don't think too much about why we are doing this. That will get clear very soon. But just try to focus on what exactly is happening. Okay, so what is happening is extremely trivial. That at every node we have a few children of the node. I pick one child and I assign and I call it my special child, and I connect a heavy edge to that child. And for every other children, I call them normal children and I connect a light edge to those children. So I am classifying my edges into heavy or light, or I am classifying my nodes as special children or normal children. Okay, this is what I am doing. Okay, and the way we pick the heavy child, the way we sorry, the way we pick the heavy child is by looking at the size of the subtree of every children. Okay, so if you notice these numbers are basically the subtree sizes. So for example, the subtree size of a leaf node is 1 because the subtree has a single node, which is a leaf node. The subtree size of this node is 2 because it has these two nodes. The subtree size of this node is again 1. Subtree size of the node is 6. It has 1, 2, 3, 4, 5, 6, so on and so forth. So these numbers which are written on top of the nodes are called like are the subtree sizes which we have pre-computed for the given tree. And whenever we have to make a choice, whenever we have to make a choice between a special child and a normal child, like whenever at any node, whenever we want to pick a like one of its child as a special child, we pick the child which has the maximum subtree size. Okay, so we pick the child which has the maximum subtree child. Okay, the child which has the maximum subtree size is picked as a special child, and every other child is picked as a normal child. So again, if you look at the example above, for the first node, the maximum, like the child with the maximum subtree size is this one. So we pick it as a special child and we create a heavy edge. For everything else, we create a light edge. Okay. For this node, the child with maximum subtree size is this one. We create a heavy edge. Everything else, we create a light edge. Okay. Similarly, for this node, the child with maximum subtree size is 4. We create a heavy edge. Everything else, we create a light edge, and so on and so forth. Okay. So every every heavy edge connects a node with its special child, which is defined by the maximum subtree, like the child which has the maximum subtree size, and every light edge connects a node with its normal child, which is not special. Okay. Is this Yeah, the order of labeling of nodes does not matter. Oh no, the order of labeling of nodes is heavy light matters. Like like you can choose any subtree which has the largest size as the special child. Okay, but once you have chosen the special child, the rest of the nodes are light, and you can do any ordering among them. But you need to choose your special child very carefully. So if all nodes have equal weight, you can choose any weight, like any node to be a special child. It doesn't matter. Yes. The numbers on the nodes are the size of subtrees. As I explained, these numbers which I have written are just for the sake of convenience. And like this image has been taken from Anudeep's blog. Anudeep is also uh, a great programmer. He's also been to the World Finals, and he originally wrote a blog on heavy light decomposition. This image has been taken from his blog. I would recommend everybody to also go and read this blog after this lecture. So I also originally learned HLD using this blog, like via this blog. Okay. So, okay, like coming back to the topic, these numbers are subtree sizes. Okay. They have like I mean these are not node numbers. These are the subtree sizes of these nodes, and they are written here just for the sake of convenience, like so that you can see visually that how we are identifying the special children and the light children of a node. Okay. So okay, so the size of the subtree, like when I say max size subtree, it is the number of nodes in the subtree. This is a good question. The maximum size subtree is the number of nodes in a subtree. Okay. Okay. So again, if you try to look at this example, for example, it is written 7 here, and 7 means that this subtree has 7 nodes. Okay. 6 means that this subtree has 6 nodes. Okay. 17 here means that this whole subtree has 17 nodes, and so on and so forth. Okay. So the numbers written on top of nodes are subtree sizes. And the way we select a special child, like for every node, we have to make a decision. For every node, we look at all the children of this node. Okay. We look at all these children of the nodes, and we want to assign one child as special child. So the way we do it is we pick the child which has the maximum subtree size, for whom this number is the highest. And if all the children have same subtree size, then we pick any one. Okay. So you pick any one of the children which has the maximum subtree size. In this case, node 17 has maximum subtree size. And therefore, it is picked as a special child. Like for this node, the maximum subtree size of a node is 7. Like, so therefore, this edge is picked as a heavy edge, and this node is picked as a special child. And all these are picked as normal children. So whenever you see a colored edge connecting a parent and a child, it means that the child is a special child. If you look at any other node, like if you look at any other node for whom the connection between its parent is uncolored, it means that the node was a normal child, and the edge is a light edge. A light edge connects a normal child to its parent. A colored edge or a heavy edge connects a special child to its parent. Okay. Doubts? Yeah, so how we determine the number of nodes in a subtree? Like using a DFS. This is standard technique. You should already know this. Okay. So now we know that every light edge connects. So now notice that the tree is actually divided into different chains, and those are represented by the colorings. So if you look, this whole forms a single chain. A chain is basically a path. Okay. Like whenever I say a chain refers to a path which goes from top to down, like which does not turn anywhere, where the starting point of the path and the ending point of the path are ancestors, like share an ancestor child relationship. For example, This is the first path. Okay, this is the second path. So if you look at all these paths, like every different color represents a different chain in the tree. So the tree has been broken down into different chains, and every light edge connects two different chains. So basically, whenever we encounter a light edge, we say that we start a new chain. So therefore, this is a new chain. Like this is a new chain. This is a new chain. A new chain. Every different color in this, like in this picture, represents a different chain. And this breakage into chains has happened because like every node we know becomes a part of a single chain. So for example, we start a chain at the root node. Okay, inductively we see that we choose one special child for the root node, and this special child is the one which we add to the chain of the root node. So therefore we include this special child in the same chain in which the parent is present. So the green chain extends to this child, and for every other children we start a new chain. So we start a new chain at this child, we start a new chain at this side, we start a new chain at this side. Okay, similarly for this node we choose one special child, which is this one, and we extend our existing chain. So we make this child a part of the existing chain. For every other children we create a new chain. So, like this is a new chain, a new chain, a new chain, okay, and so on and so forth. And we keep doing this everywhere. So, therefore, we can see that every node becomes a part of exactly one chain, and the whole tree is broken down into vertex disjoint chains. Okay, is it clear to everybody? So, don't worry about what we are trying to minimize. Like we'll come to that. Okay, so we'll come to the fact that why we are doing this. Like it will get clear very soon. Just try to focus on what exactly is happening. Okay, so HLD is a method of decomposing the tree into chains. Okay, so if so what we are trying to do here is, again, like if you try to see, like I will try to show you by some example. Okay, so let this be node 1, 2, 3, 4, 5, 6, 7, 8. Like I'm trying to assign some numbers to these nodes, like so that it's easier to visualize. These numbers are different from the numbers already written. The numbers already written are subtree sizes. Like the numbers I'm assigning now is just for, or maybe I should assign A, B, C, D. I'm not sure. Yeah, I think that would be better. Okay, so so I've assigned some label to every node, and if you try to visualize what is happening, we pick this largest chain. What HLD tries to do is you pick this chain first, okay, and you put it into an array. You put it into an array. So your array will have the first element as A, second element as B, third element as I, fourth element as O, fifth element as V, and sixth element as T. Okay, so A, B, I, O, V, T. All these will become the first five elements of your array. This is your linearized array. Okay, so this is the end of the first chain. Every chain becomes a part of the, like every chain is picked up, like you pick up, like you imagine a chain as picking it up from the head and putting it into the array as a linear ordering. So like you put this chain as a linear segment into your array, into your linearized array. Okay. Then you do the same thing for the next chain. The next chain you can pick arbitrarily. Like it doesn't matter much how you do it for HLD, but if you're doing DFS, then by default like your DFS would first go to all the heavy children, because and then you come back, like you consider this particular node, like this is like this is a node with a, like this is a chain with a single element, so you put it next. Okay, so you put it, you put U here, then you again come back, you take a look at this particular chain, like this is a chain with two elements, you put both of these elements together next, so you put N and S next, and so on and so forth. Okay, and to give you guys an understanding of what is happening, like these belong to the light green chain, then this guy belongs to, yeah, the brown, whatever color this is, the brown chain. Like basically, like you belongs to this chain. Then NS belongs to the orange chain. Okay, this orange chain, and so on and so forth. So every chain in your tree becomes a linear segment in your array. Okay, so you in HLD, you first step one is to divide your tree into these chains by assigning every child as a special child or a normal child, and like you break your tree into these chains, and then the second step is to take these chains and put them as linear segments in your array. So you have this chain, you have the next chain, you have the next chain, and so on and so forth. Okay, so you assign them as linear segments in your array. So this is a visualization of what exactly is happening, and then we can go and look at some properties. Okay, yeah, I mean, like, don't worry about the orderings. The ordering is important. The ordering is important in the sense that you should be considering all elements of a chain together. So you should pick all elements of a chain and put them together. After this, like you need to go and pick up the next chain. The next chain can be anything. I just picked this one and put it here, and then I picked this chain and put it here, and so on and so forth. So the important part is that once you have decomposed this tree into chains, you need to go and pick a chain and put it as a linear segment in your original array, like in your linearized array. And you have to keep doing this for every chain one by one. But which chain to pick in what order, that is not important. Like what is important is that you pick every chain and put it as a linear segment together. Okay. Does it answer your question, Rahul? Uh, so we do DFS only for special child. Okay, don't worry about it. Like we look at the implementation. Don't worry about the implementation right now. Is it necessary to pick the longest chain first? Again, it is not necessary. It is just a part of implementation. You can pick any chain, but the idea is that once you pick a chain, you should pick all elements of that chain and linearize it into the array. Okay, Nandini? Yeah. Like let's not worry about the implementation right now. Okay, so is it clear to everybody so far that what exactly is happening? Like we'll also look at some properties of this structure and discuss why this is useful. But first, the idea is to be able to visualize it correctly. Like so, I mean, like one of the reasons I enjoy doing graphs and trees is that you can really visualize what is happening. So like we will discuss the advantages. Don't worry about it. But for like right now, just try to visualize what is happening. Just try to visualize uh, like the fact that you are given a tree, you are breaking it down into some chains, like using the whole heavy child and light child property. And once this decomposition into chains is done, you pick up each chain and you put it as a linear segment in the array. So you have an array which is composed of different segments, and every segment is a chain in the original tree, going from top to down. Okay. These are like this is the core visualization of HLD. Once you have this visualization in your head, after some practice, like you'll be able to solve any questions. Okay. Yeah, you can pick the next chain in any order. Like we will discuss the implementation later that which order is recommended. But like for the theory, like you can take it in any order. It doesn't matter. Like the theory is still as solid as. Uh, yeah. I mean, the theory does not depend on any ordering. Okay. Okay. So like let's move forward to some properties and see like whether we have understood the concept or not. Okay. So let me ask you guys a question first. What is the uh, maximum, like I will create a poll, so don't answer this in chat, like so that others can also uh, participate without worrying. So what is the maximum number of chains that can occur in a tree of n nodes. And you have four options. Option A is log n, option B is root n, option C is n, option D is n square. Okay. So the question is that what is the maximum number of chains that can occur? Like if you do this decomposition, what is the maximum number of different chains which can occur in a tree of n nodes? I'll create four options. Like I'll create a poll. Okay. So I have created a poll. Please answer the poll. The question is that if you do this decomposition, what is the maximum number of chains? Like what is the maximum number of different chains? So for example, in this tree, how many different chains we have? The number of different chains is equal to number of different colors. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are the number of different chains we have in this particular tree. Or the number of different chains can also be equal to the number of light edges, because we know that every light edge connects two different chains. So the number of light edges can be equal to the number of different chains. Okay. So please answer your questions. Like don't answer them in the chat. Like please answer them in the poll which I've created. Yeah, you can assume there's an order here. Like I don't expect an exact answer, but like order log in, order n, order root n, or order n square. Okay. So the poll vanished. Uh, yeah, apologies. I think I created a poll with a shorter duration. Okay, I'll create a poll again. Please answer the questions if you haven't. Yeah, please answer it again, even if you've answered it before. But please answer the question again. Okay. The options are A is log n, B is root n, C is n, or D is n square. So, like many of you are answering C, which is also the correct answer. So, if you want to look at an example, you can look at a like you can look at what is called a star graph. So, for example, this is a star graph. A graph like a tree which has a single node in the root, and all the n minus 1 nodes are the children of this root node. So you have a root node 1 and you have all other nodes as children of the root node. In this case, if you go and do the decomposition, how will it look like? You will start at the root node, you will select a special child, and you will mark this as a special child, and everything else like will be marked as a normal child. So you will be starting a new chain for each of the other leaves. So you will have total of n minus 1 different chains, because the root node and one of its child will be in the same chain, and every other child will be part of a new chain. So you will have n minus 1 different chains in this case. So therefore maximum the maximum number of different chains you can have is n minus 1. And like the reason I said order n, because uh, yeah, I mean if you have like a tree with a single node, say n is equal to 1, then the number of different chains is also 1. So in this case the number of different chains is equal to n. Okay. But anyways, okay. So is it clear to everybody that how did we arrive at this answer of n nodes, like of n different chains? Okay, great. So now let's look at some properties of HLD. So the first property is that every vertex is part of exactly one chain. This is a trivial property because like the way we are decomposing our tree, we know that for every vertex, either the vertex is part of the chain in which its parent lies, or it is part of a new chain. If it is the root node, or if its parent edge is a light edge. So like there are only two options. One, if the vertex is part of the same chain in which its parent lies, this happens when the parent edge is a special edge, or the vertex is part of a new chain Like this happens when the parent edge is a light edge. So every vertex is part of exactly one chain. And like the next property is that every chains forms a subarray in the linearized tree. This is by definition. I mean, we like this is what I told you that like once you do HLD, like once you have done this decomposition, like the next procedure is to pick up the chains, pick up every chain one by one, and put the whole chain as a linear segment in your linearized array. So you put it as a subarray in the linearized array. Okay, so you put it as a subarray. Like this subarray represents a given chain. So your linearized array is basically composed of a concatenation of different subsegments where each subsegment forms a chain in the original tree. Okay, so both these properties are trivial by definition. Let's move forward to the next property. So this is the like this is now a very important property that the subtree size reduces by at least half on traversing a light edge. Okay. So what we are trying to say here is that suppose this is a node and suppose this node has say some m children. Okay. How do we select the special edge? We say that an edge is special. Say this is special if the subtree size of the special child is highest, like is maximum. Okay, is maximum. So if a node has m children, what is the minimum, like what is the minimum subtree size which the special child would have? My SC represents my special child. My sub of SC represents the subtree size of my special child. Okay. So the claim is that the subtree size of the special child has to be at, at least greater than the subtree size of the node. Like say this is the original node n. The subtree size of the node divided by m, where m is the number of children. Number of children of the node. Okay. Is this property clear to everybody that why this is the case? So the subtree size, the subtree size of the maximum child is is at least the subtree size of n divided by m. Why? Because even if you want to like the subtree size of n is basically the sum of all nodes which lie in the subtree of n. You want to distribute this sum into m children. Okay, into m children. You want to distribute this sum into m children. So what is the and you have a special child. Now the special child can have a minimum, would have a minimum uh, subtree size of at least subtree by m. Why is that the case? Like this will be the case if you distribute your sum of n equally among all the m children, equally among all the n children. If all of these have subtree size n divided by m, this will be the optimal distribution where your special child will have the lowest subtree size. Any other distribution, your special child will have a subtree size of more than sub of n by m, and other children will have a size less than sub n by m. So like this is the first observation, and the second observation is that because of this, the subtree size of any normal child has to be less than equal to the subtree size of n by m. Why? Because the subtree size of the special child Okay, let me actually write a better thing. So for any normal child, we know that the normal child, like the size of this normal child will be the sorry, the subtree size of n minus the subtree size of, like the subtree size of the special child divided by m minus 1, because there are at least m minus 1 normal children. Okay. Actually, no, this is not correct. It's not divided by like normal children. So basically, this is what is left, like that you want to distribute among normal children. But normal child also has to be less than the special child, because the special child was the one which had the maximum weight. Okay. So like we can also try to look at another different, like maybe an easier method to prove this. So let this be any node and let it have some children. Okay. The claim is that if this is a normal child, the subtree size of the normal child should be less than equal to subtree child of the node n divided by 2. Okay, this is the claim. Maybe you can forget about all of this. Okay. So this is the claim that subtree child of a normal child, the subtree size of a normal child has to be less than equal to half of subtree size of the original node. That subtree size of like reduces by at least half on traversing a light edge. On traversing a light edge, you reach a normal child. Okay. I'm saying that let's try to prove it by a contradiction. So assume that there exists a normal child whose subtree size is whose subtree size is more than n by 2, like the subtree size of n divided by 2. Okay, suppose this exists. Sorry. Then what would be the subtree size of the special child? The subtree child, like the subtree size of the special child can be at most the total subtree size minus the subtree size of this normal child. Like can be at most n minus what we have already assigned to this particular normal child. Okay, and we said that this quantity is more than sub of n by 2. Like this is what we said in the first statement. We assumed this. So if this quantity is more than sub n by 2, sub n minus sub n by, like sub n minus a quantity more than sub n by 2 will lead to a quantity which is less than sub n by 2, right? Because you are subtracting more than half of the same quantity. So what you get is that subtree size of SC is less than equal to half of subtree size of n by 2. This implies that subtree size of SC is less than the subtree size of this normal child, because like for normal child the subtree size was more than n by 2. For the special child it is less than n by 2. So therefore the special child subtree size is less than the normal child subtree size, and this is a contradiction. This is a contradiction because we assumed that the special child is a child which has maximum subtree size among all children. So the subtree, actually, this is a strict inequality, because like there's a strict inequality here. Okay, so the subtree size of the special child cannot be less than the subtree size of a normal child. So therefore this leads us to a contradiction. Okay, is it clear to everybody? So like this was a proof of why the subtree size will reduce by at least half on traversing a light edge. Like if you don't fully understand it, Like you can also take it as, say, like something which is true by default, like as a fact. This is not needed for implementation purposes, but it is good to know. And the proof is not very hard. Like it is a simple assumption that if you if you look at, like if you assume that the subtree size of any normal child is more than n by 2, you get a contradiction that the subtree size of the special child will be less than that of the normal child, which cannot be true by construction. Okay. So once we have this property, like here is where the true power of HLD shows up. Okay, because of this property, we can prove that we can go up from any node x to any of its ancestor node p. P here can also be the root node of the whole tree. You can go up from any node x in the whole tree to any of its ancestor node p by changing at most order log n chains. Okay, by changing at most order log n chains. What does it mean? Like, to give you as an example, suppose you want to go from node 1 all the way up to the root. How many different chains do you have to change? How many different chains do you have to change? You have to change only one chain, because you traverse this one light edge. All these nodes belong to red chain, and both of these nodes belong to green chain. So therefore, you have to change the chains only once. Okay. Similarly, if you want to go up from this node all the way up to the root, you will have to change the chains twice. This is the first chain, then you do one hop, like you traverse a light edge and you change the chain. This is the part from the second chain, like this is the part from the second chain which you utilize. Then you again change a chain, go up, and you use these two nodes from the third chain. So you change the nodes three times. So sorry, I mean you change the chains three times, like two times, and you change the chains and you traverse a total of three different chains. Okay. So this is what I mean when I say that you can go from any node to any of its ancestors. Suppose you want to go from this node to this ancestor. How do you go up? Chain 1, chain 2, chain 3. Okay. Chain 1, chain 2, chain 3. So again you have to change the chains twice. So similarly, the claim is that you can go from any node X to any of its ancestor node P by changing at most log n chains. Okay. This is the claim. This is the claim. So is it clear to everybody, like what we are trying to show? Like what is the claim here? N is the total number of nodes in log n. N is the total number of nodes in the whole tree. So like when we talk about log n, it is the total number of nodes in the whole tree. I don't expect that you, like, I am still to prove that why this is true, but the question here is that is it clear that what is the property? Okay, the property here is that we will be able to, because of this property, because of the fact that the subtree size reduces by at least half on traversing a light edge, which means that if you go from this node to this node, the subtree size of this node is at least half the subtree size of this node. Okay, so whenever you traverse a light edge, whenever you go from a parent to a child, like whenever you go from a parent to a normal child, the subtree size of the normal child is at least half the subtree size of the parent child, like of the parent node. This is the third property. And because of this, we can show that to go up from any node X to any of its ancestor nodes P, we can do this by changing at most order log n chains. Okay. And why can we show this? The proof is extremely simple. So what do we mean by changing a chain? Changing a chain means that we are traversing a light edge. A light edge. Because whenever you change a chain, you are basically moving across a light edge. Like every light edge connects two different chains. So whenever you want to hop from chain 1 to chain 2, you have to traverse a light edge. Okay. Sorry. And you know that whenever you traverse a light edge, the subtree size of the parent node is double the subtree size of the child node. Or the subtree size of the child node is half the subtree size of the parent node. So subtree of parent is 2 into subtree of the normal child on traversing the light edge. Okay. So therefore, you can traverse at most log n light edges. You can traverse at most log n light edges. Okay. And why is this true? Because suppose you start from a leaf node whose subtree size was 1 and you want to go up all the way up to root. Whenever you traverse a light edge, that is, whenever you change your chain, your subtree size at least doubles. So if for the leaf node subtree size is 1, on traversing a light edge, it will become 2. Again traversing a light edge become 4. Again traversing a light edge become 8, and so on. It will grow in the power of 2 to the power k, like will be your subtree size, where k is the number of light edges traversed, or the number of times you have changed your chain. And because we know that the total subtree size has to be less than equal to n, we know that 2 power k has to be less than equal to n. So therefore k has to be less than equal to log of n to the base 2. Okay. So therefore, by changing at most log n nodes, you can reach from any child node to any of its parent node. Okay, this is the important property of HLD. Is it clear? Any other doubts? In terms of applications, so I've already motivated the use of HLD earlier. Like maybe we'll have some time to look at examples and look at some questions. I'm not sure, but we'll give some practice questions later on. Okay. Yeah. If you do some practice, I'm sure you'll get used to identifying where to use HLD or not. Okay. So like you can also again like you should spend some time yourself as well. But like this is the important property that if you try to remember this as a fact for now, that going up from any node, like any child node, to any of its ancestor can be done by changing at most log n chains. Okay, and every chain was a continuous segment in your original array. Like this is by construction, that every chain is a continuous segment in your original array. So therefore, the last property, that any path AB can be written down as a path from A to LCA and LCA to B. Like this is a very standard thing, that if you have two nodes A and B, like you can write down the path from this node, like the path between these two nodes as, like this is node A, this is node B. Like you can write down the path between A and B as the path from A to LCA and LCA to B, where LCA is the lowest common ancestor. Like this is the LCA node. Like this is the lowest common ancestor between A and B. Okay. So how to find the LCA? Like maybe I can send some resources if you don't already know about this. But like this is again a standard technique. So you can break down the path between any two nodes A and B as the path from A to its LCA and LCA to B. And notice that both of these paths are of the form A to an ancestor and B to an ancestor. So therefore, these two paths we know can be traversed by changing at most 2 into log n chains, like 1 log n for each of these two paths. So therefore, any path from A to B can be written down by traversing at most 2 into log n chains. Okay. And these 2 into log n chains therefore correspond to 2 into log n segments, 2 into log n segments of the form L comma R in linearized array, because every chain is a continuous segment. So therefore, any part of a chain is a continuous segment LR in the linearized array. So if you are changing at most 2 into log n chains, you are looking at most 2 into log n different L comma R entries in your linearized array to represent your whole path from A to B. Okay. So this is the property that makes HLD very, very powerful. And because we know how to process a single LR range in an array. Now, instead of processing one L comma R range, we need to process 2 into log n L comma R ranges in array to answer a single query. And the processing of one range can be done in order log n time by a segment tree or like whatever other DS you might want to use. So now we have an additive log n factor here because we are doing it log n different times. So like we are doing a order log n query on segment tree, order log n different times for each of these log n different chains. So therefore the total time taken by this whole procedure for a query or update would be order log square n. Okay, this is the whole idea of HLD. So the size of the longest chain can be anything, but the like the log n factor which I'm talking about is the number of different times you will have to switch between two different chains. That number will be log n. The number of different times you have to switch between these two chains, like any two chains, will be log n. Okay. Are people able to follow so far? How many of you are not understanding anything? Okay, like please give some feedback if you like if you are following so far, or at least if you are following most of the things so far. Like you can obviously revise the proofs later on, or like review the details later on, but it is important to understand the core concept. Like only then it would make sense to move forward. Okay, great. So now the step like if you try to summarize the steps to support path updates and path queries in a tree, the steps are as follows. First step, you decompose the tree into chains via HLD. Like after this decomposition, you should have this coloring of your tree into different colors. The second, you linearize the chains into an array and build a data structure on the array that supports the range queries and updates. This DS is usually segment trees, but it can change based on the problem. For example, okay, let's not go into more complex examples. But yeah, usually like this DS is segment trees. Third step, for any path query or update between two nodes A and B, we process it as a query or an update on the login different ranges which are present in the linearized array. These login different changes, these login different ranges come because we have proved that we can go from any node A to its LCA by changing at most login different chains. And every chain is a continuous range in the linearized array. So therefore, because you are changing at most login different chains, you are considering at most login different ranges in the linearized array. So therefore, these ranges correspond to the login different chains that we need to traverse while going from A to LCA and LCA to B in the original tree. So therefore, the total time taken will be order log n into the time taken by the linear DS. This DS is usually segment trees and takes order log n time. Okay. So if this dx takes order log n time, your total time taken will be order log square n, which is also pretty good. Okay. Is it clear to everybody? Should we move on to some implementation? Do you guys want to see some code, or should we continue with the next topic's theory? I think we are slightly running behind time. No, log square n is not pretty there. It is fairly common. Okay, so let's quickly go over some code pieces. Okay, I will like maybe quickly share the code, and I'll of course also share the code like later on. So are you guys able to see my screen? Like are you guys able to see to read the code correctly? Like is the zoom level and everything perfect? Okay, great. So like I usually implement it like this. I know there is a couple of better ways of doing this, which I've recently looked at. but I haven't had the time to modify my own implementation. But like this has worked pretty well during my 4 years of practice. So like I can go over this right now, and maybe I can like send you guys a better version like later on. So I call this preprocess function. Uh, this is a sparse table DP, which is usually useful for computing LCS. You can ignore this. The first DFS, sorry, the first DFS is done to compute subtree sizes. Like, so this DFS is responsible for computing the subtree sizes. For those of you who don't know, the way I store my graph is, sorry, is what is called an edge list. I have shared some examples of this probably in earlier classes, but I'm not sure if all of you have attended that. So I scan my edge. So my UI, VI, and WI represents a single edge I going from node UI to VI with weight WI. Okay. So ith edge, I have a numbering of my edges. My ith edge goes from a node U of I to V of I and has a weight W of I. Okay. And the way I store my graph is that I have a vector of, uh, I have a vector int say G of N. Here my, like, and when I read my edges, I do G of U of I dot pushback I. Okay. This means that I have a edge list for every vertex. Like this is a hybrid combination of uh, uh, like the usual adjacency list. So usually we do g of x dot pushback y, which means that node x and y are neighbors. But here I am doing g of x dot pushback e, where e is the edge number of the neighboring edge. So therefore, the ith edge is basically the edge number, and the ith edge is the neighbor of node u. Okay, and I have another function uh, which is called like which takes a node and a edge number, and it returns, sorry, it returns this. Like so, this is basically the it returns node adjacent to x on the edge e. Okay, so it assumes that like one of the endpoints of the edge e is node x, and you want to find the other endpoint because it is an unweighted graph. So like you will be pushing back your ith edge in both gi and vi, like because it is an undirected graph. Okay, so you have this adjacent function. Now given these things, like you want to do your first DFS to compute the supply sizes, you iterate on all the edges adjacent to the given vertex. You check whether the edge is equal to the parent edge. If yes, continue. If not, you compute the adjacent vertex. You increase its level. You do a DFS and you add its supply size. Like so, this is a standard DFS to compute supply sizes in a given graph. And then I have like what I called the chain heads and chain parents and chain numbers. So like for my chains, I represent a chain as a chain, like I have a chain parent which uh, like represents which node is the parent node of a chain. So for example, sorry, one second. Yeah, I think my device got hung. Okay, sorry. Yeah, so for example, like for this chain, this node will be its parent because like from this node, we traverse a light edge and start this chain. Okay. So this is like this is the definition of a chain parent. A chain head is the topmost node in this chain. The chain number is like the number of the chain. The position of this node is the position of the node in the linearized array. and I have a number of chains, and I have a buffer length. So I have this single DFS function called HLD, which, like, whenever we enter a root node, I add this I add this node to my linearized array. In this case, I'm adding the weight of the edge. Like in this case, I'm adding the weight of the parent edge. I can also add the weight of the current node or any other property that I want to add. My base array is my linearized array. I have my b length as the buffer length. I mark that this node occurs on the position b length in my linearized array. I increment my b length. I mark the correct chain number for the current chain, and then I try to find the special child. Like I write this loop and compare the subtree sizes to find the special child SC. Once I have the special child, so if there is no special child, it means that, like, the node is a leaf node, so I just return. If there is a special child, I first do an HLT on my special child. uh, so I continue the current chain number, because, like, when I do the HLD on special child, my chain number remains the same. So I don't need to change my end chain. And once I have returned from this HLD, I do a DFS on the other children, which are the normal children. So I iterate on all the edges again. If it is a special edge, like if it is a heavy edge or a parent edge, I ignore it. If not, I look at the normal child. I increment my chain number, because every time I visit a normal child, I am creating a new chain. So I increment my chain number. I mark the parent and the head of this particular chain number, and I call HLD on the normal child. Like, so this is like, this is a simple DFS function, like, using which you can do the linear, like, you can do the marking. You can make sure that you have your nodes linearized into this base array, and for every node, you also have the position of the node in the linearized array, and you have other things maintained, such as chain head and chain parent, which can help you traverse between the LR ranges. Okay, so you can look at this. Like, this was the a brief overview of the code. Yeah, I'll probably also share the code later on, so that you can spend more time on this yourself. uh, okay, should we proceed to the next theoretical part, because I think we are also running out of time, so it would be good if we can discuss, say, the Euler 2 technique. Okay. Yeah. So I'll share the code piece. Like, don't worry about it. Like, maybe if I have some time, so I won't have time today. I have 2 or 3 more lectures. But maybe I can spend some time tomorrow, and like, code up a question which, uh, like, using HLD, and send you as the code. I don't want to send my earlier accepted codes, because the yeah, I don't uh, like, remember, like, I want to send like, something which is simple, uh, to understand. And yeah, this type of graph, so HLDs, yeah, like, this type of graph presentation is generally very useful. Again, like, there are material benefits, but maybe it is beyond the scope of this class. Okay, let's proceed to, I think, the Euler 2 technique. Okay. So now we have covered how to do path queries, like how we can do path queries on a tree. Like, the next topic for today is how to do subtree queries on a tree, or subtree updates on a tree. Okay, so now we look at a technique using which we can represent every subtree as a continuous segment on a given array, like on a linearized array. So we want to linearize our tree. Suppose this is a given tree. The image has been taken from Wikipedia. So it is called Euler 2 technique. Like, you can, given any tree, you can linearize this tree into an array, such that any subtree, like any subtree for node x, corresponds to a single range L comma R, in the given array. So a subtree corresponds to a single range. Okay, and once this correspondence is done, you can just do so. Like, because the number of ranges are order one, like, you can, like, exactly one, like, not order one. So you can do your query and updates very similar to how you do it on a single array. So, like, there's no, like, extra multiplicative factor like we had in uh, HLD for, like, for supporting subtree queries and updates. Okay. So, like, how we do this? So there are two ways we can do this. Like, way one is that we insert every node twice in the linearized array. Okay. both the approaches have their own pros and cons, but like let's just try to understand the approaches one first. So in this case, so what we do is that we do a simple DFS, like we do a simple DFS on the tree, and whenever like and we maintain a global timer. Okay, like we maintain a global timer. We increment the time whenever we enter a node and exit a node. So whenever we enter a node for the first time and whenever we exit the node for the last time, we increment the time and we insert this node in our linearized array. So for example, like if you look at this particular tree, I mean the same thing is also true for edges. Like you can also think the same thing for edges. So for example, if you look at this tree, you start from the root node and you do a DFS. The first time you go to the left child. Like yeah, and this is a random ordering. Like right now, I'm not defining any particular ordering in the DFS. Like, this can be a random ordering. In this particular example, the ordering is such that you go to the left child during your DFS. So you encounter the edge one for the first time. You push it into your linear array. Okay, and then you have this node. Again, you do a DFS, you go back to the left child, you encounter H2 for the first time, you push it in your like linearized array. Like you reach this node, you go down, you push 6 into your linearized array. Now, while going back up, you again encounter the node 6, like or H6, you push it again into your linearized array. Again, you go up, you push 2 into the linearized array. You go down, push 4, go up, again push 4. Okay. Again, you go up, again you push 3, go down, push 3, go up, go back up, again push 3, go back to 5, we go down to 5, push it, go back up, again you push it. So, you insert every node or every edge in the Euler tooth array. Like this is the linearized array. Okay. So you push every node or every edge in the array whenever you first enter the node and whenever you last exit the node or last exit the edge. At that time, you push that node or that edge into your linearized array. So every node and every edge, like every node or every edge, whatever you are maintaining, you are maintaining this for, of the tree will occur exactly twice in the Euler tool array. Because while doing your DFS, so suppose you have a node like this, okay, and you are maintaining the Euler tool for nodes. Then node 1, 2, 3, 4, 5. Your Euler tool would look something like 1, 2, 3, 3, 4, 4, 5, 5, 2, 1. So notice that I pushed my node 2 after I traversed all the children of 2. So node 2 in this case have 3 children. So in the actual DFS, I would have come from 1 to 2, gone from 2 to 3, come back up, gone from 2 to 4 down, come back up, gone to 2 to 5 down, come back up, and then again gone back up. So I push 2 whenever I first reach 2 from its parent and whenever I go from 2 back to its parent. Okay, so this is the definition of entering the node or exiting the node. Okay, so therefore, by construction, like we can see very obviously that every node will occur exactly twice in the Euler two array. This is by construction. And what would be the and for given any node x, the indices at which it occur, I will mark them as start of x or end of x. These are also marked as in of v and out of v. In of v means the time at which we first entered v, and out of v means the time at which we exited v. These will correspond. I mean, these times are basically just indices of node v in the linearized array A. Okay, so these are just indices of node V in linearized array A. Okay. So if you try to look at this example, like for every edge, what would be the start and end time of the edge? Like for one, the start time of this edge would be one. I'm assuming a one base indexing. 1, 2. Okay. And what would be the end time? It would be 8. And you can also see this by like either looking at the indexes of A or looking at the time at which you actually come back. Assuming that you increment time whenever you enter a new node or whenever you exit a new node, you increment your time. Okay. So for 2, the same thing would be at 2 comma 5. 6 would be at 3 comma 4 because like I increment the time whenever I enter 6 and I decrement whenever I increment again whenever I exit 6. Okay. So for 4 it would again be 6 and 7. Okay. And so on and so forth. Is it clear to everybody? Should like so sh- uh, people are saying like Shahid is saying that please discuss some applications. I'm not sure, Shahid, if you were present in the beginning of this lecture or you joined in the middle. But if you look at the beginning of the lecture, I did discuss the motivation that what exactly we are trying to do. In the Euler 2 technique, we are trying to support path query like subtree queries and updates, and in HLD we were trying to support path queries and updates. I will link you guys to some hard problems on Code versus CodeChef if you want, but I think that would take up unnecessary time of this lecture. Like you can look at those problems after the lecture as well. But like I think I've tried to motivate like the use case at the beginning of this lecture. I'm not sure if you were present in the beginning or not. Okay. So ETT adjacency. This is the representation of the tree. ETT is a way of linearizing the tree. They are two different things. After it again enters two, so two should be incremented. No, so after 4 it does not enter 2. Like 2 in this case is on this edge, but even if you consider a node, like for the node you will increment the timer when you enter the node from its parent and when you exit the node and return back to the parent. Whenever you reach the node again, coming back from its children nodes, like you don't worry about it. Okay. So for every node or every edge, so you will be doing this either for nodes or for edges depending on what you want to support in the problem. So like for both of them, you will increment the timer only when you enter it for the first time and exit it for the last time. Okay. Okay. Is it clear to everybody what exactly we are trying to do here? What is a double order traversal? I'm not aware of this term, like double order traversal. Like maybe you can ask in Discord and we can discuss it later there. Gautam. Okay. Okay, so like so far, I'm just asking you, is it clear what is happening? Why it is happening? Like what is the use case? We are still yet to come. But what is happening should be clear. That we are doing a DFS, and every time we enter the node for the first time, we increment our timer. Every time we exit the node for the last time, we increment our timer, and we push the node in our linear array. Okay. So now, if you look at this representation, the reason we did this was that so for every node, we maintained a start time and an end time. The start time was the first time this node was pushed in the array, and the end time was the last time this node was pushed in the array. The observation now is that all the nodes which lie in the subtree of a node X, all the nodes which lie in the subtree of a node X, or a subtree of a node X, is now represented by a continuous range in the linearized array depicted by start of X to end of X. Okay, so a subtree of node X is now represented by its in time and its out time. Like this is the linear range L comma R, which contains all the nodes which are present in the subtree of this node. Okay. So if we try to take a look at an example, Okay, so sorry. So like for example, for this particular node, the start time and end time are 1 and 8. Okay, 1 and 8, and all the nodes which occur, or all the edges which occur in the subtree of this tree are 2, 6, and 4, and they are present in between 1 and 8 in this linearized array, and only these are present. Okay, so if you look, 2 occurs twice, 6 occurs twice, and 4 occurs twice in this linearized array between 1 to 8. Okay, so the reason, like, I mean, the reason this happens is because we are doing a DFS, and the way DFS is supposed to work is that when you call DFS on X, DFS on X traverses the whole subtree of X and then returns. This is how DFS works by default. Okay, like whenever you call DFS on a particular node, it is called depth first search. It means that it will search the whole subtree of this node X, and only then this recursive call will return. And we say that start of X is the first time DFS is called on X, and end of X is the last time, or like the time at which all nodes in the subtree have been explored and DFS is returning. Okay, so when DFS is returning from node X, so DFS has explored all nodes in